Tornamos ahí, ¿no? Como Isabel, te dejo ver.
Claro, sí, sí. Soy chiquitilla, pero
No se equivocado.
So good afternoon, everyone. So thank you very much for being here. So it's my pleasure to introduce Pedro Rivero. So I guess that all of you know about the strong collaboration that is going on between IBM and the Basque research centers on quantum computing. So Pedro Rivero, he comes from IBM. Actually, he's an engineer, but also a computational physicist, right? So he made his undergraduate studies in Madrid in the Polytechnic University. Then he moved to make his PhD to the US, to Illinois, to Chicago. So he was working in the Illinois Institute, working on developing his PhD in the Illinois Institute of Technology, collaboration also with Argonne National Lab. And then he moved to IBM, where he has been already for, I think, 2-3 years, something like that. And I think he's one of the main helpers for us in everything that is linked to quantum computing. So we are very fortunate to have you here, Pedro. Thank you very much for coming. I know it's your first visit here, but I hope it's the first of many, right? So thank you for being here, Pedro.
Thank you so much for.
Sorry, just one comment. So we also have online viewers. So at the end of the talk, we will have some questions, answers. But you that are online, please send your questions to the chat or to the question and answer section.
Right. Well, thank you so much for the nice introduction. It's a pleasure to be here today. As he already mentioned, I'm here coming from IBM. I've been working at IBM for a couple of years, and my main focus have been on developing error mitigation techniques so far. So I want to give you kind of a little bit of an understanding in this talk of where quantum computing is today, what is the kind of thing that we're doing at IBM, and the kind of thing that we're really good at doing, right? And how you can actually use your recently acquired capabilities in the form of access to our very best computers, and hopefully next year your dedicated device to achieve research which really few people in the world can actually do these days, right? I've been talking to some of you before, and I think I have content for like 3 hours, so it will be probably a very brief presentation, and then I'll move to a demo just to show you some of the things that we can actually accomplish. But please feel free to interrupt. I don't expect to cover everything. Again, if someone's interested, we can talk further afterwards. But I think it's probably better if we have kind of like a dynamic conversation here, and I can answer all the questions that you have. All right, so let's get started. That thing that you see over there is kind of like our latest quantum computer. Pretty much all that you see over there, like from here, basically all the way to here, this is just for refrigeration. The chips are very, very small, are actually this size, more or less, and they all live in these boxes here. In this case, this device can actually hold 3 different chips that are then interconnected with each other. So just so you know, once you have the device here in the Basque Country, you will probably have one of the coldest places in the entire universe in the Basque Country, right? The temperature around here is in the order of millikelvins. So just so you know.
Let's see. I think the first one never works. I don't know why.
Yeah, there we go. Perfect. All right. So why quantum computing, right? How many of you are already familiar with quantum computing? And can I have a show of hands? All right. So a fairly decent amount of people. So the whole idea, and I'm just going to say this for contextualization of what's coming next. The whole idea of quantum computers is that they will enable us to solve certain problems which are not accessible using classical methods, right? We have all seen great advancements in the previous years on technologies like GPUs and HPC and supercomputing. The whole promise of quantum computers is that no matter how much progress we make on the classical side, there will always be problems which will not be able to be solved using these classical techniques, right? And those are the kind of problems that we're trying to address using quantum computers. But within those problems, right? And if there's something that I want to get out of this talk, within this broad category of problems that we can solve with quantum computers, there's a hierarchy, right? There are problems and problems. Some of the problems are more relevant than others, right? And this is a very, very important thing for reasons that I will elaborate on later on. I think this is kind of like the first two divisions. I think they're like a no-brainer. Everyone can agree with those, right? We have solvable problems with quantum computers, so things that we can solve, right? But then not all the problems that we can actually solve with quantum computers are necessarily interesting problems, right? For instance, there are problems that are already addressed with classical machines and that may invest millions of dollars in getting a quantum computer to solve those problems that we can already solve with classical hardware. That's just not interesting at all, right? What I'm here to tell you, and this is kind of what I want you to like engrave in your minds, is that out of the interesting problems that we can solve with quantum computers, there's yet another subset, another subcategory, right? And those are the problems that today are timely, right? Are timely for the field. And if you actually want to make impact in the field, those are the kind of problems that you should be looking at, right? There are many, many problems that are fantastic from an academic point of view, right? And intellectually, they might be thrilling and even beautiful. But the success of the field, and maybe to some extent survival, depends on all of us together, IBM, and in this case, you guys, addressing the problems which are timely, right? This is what's going to take you to the next level, and this is what's going to make you a referent in the field, right? Which is, at the end of the day, I believe what we all want, right? Any questions up to this point? Right, nice. I'm happy that there's no controversy so far. All right, so IBM Quantum has existed since 2016, and ever since then, there have been, probably this number is bigger today, but in the order of over 2,000 research papers published using IBM devices and IBM software, right? Now, these are just some examples. Now, very recently, we made available hardware which has over 100 qubits, right? Now, the big problem that we were facing when we introduced this sequence of over 100 qubits is that, oops, if you actually take a look at the literature, and this is a study that somebody did on all the papers published on the archive, right? What we were seeing is that, sure, we were giving people access to 100 plus qubits, right? But pretty much all the research that was being done was around 10 to 20 qubits, right? So what were the issues there, right? Why was this happening? And like everyone seems to be saying, oh, you know, quantum computing, we need to have more and more and more qubits in order to do things that are actually interesting, right? But then at the end of the day, we make it available, and people were only running research on 10 to 20 qubits, right? And I hope that with this, you start seeing kind of differences between the problems that were interesting, right? And the problems that are actually timely, right? Many of the problems that live here may be very interesting, but probably the problems that are timely should live somewhere along these lines, right? Problems which actually use a large number of qubits to show computational power beyond classical capabilities, right? If we were to continue this trend, right? Someone did that extrapolation, it kind of shows that we would not reach this 100 qubit regime until around the year 2039, right? So it would take tens of years to actually get there. And this is, of course, a problem for the field, because the field, as you are all very aware of, depends on funding. And if we don't show that we're actually doing something valuable, then why bother, right? So last year, not even a year ago, actually, IBM published in the cover of Nature a paper showcasing the utility of quantum devices, of these large quantum devices, to solve problems that live within this higher number of qubit scale, right? They basically showed that for certain expectation value problems, right, run on 127 qubits, they could actually get results which were beyond brute force classical computation, right? Now, there has been a number of articles where people actually were capable of reproducing the results from that paper using classical techniques, but those techniques were very, very smart, right? And even the people doing that actually acknowledged that if you were to change the problem slightly, that would not be a problem for the quantum computer, but the classical techniques that were used to to hack the way through the solution would no longer be amenable, right? So this is kind of the state of the art. And just to show you what that paper meant, what you have here is one of the very first circuits on the scale, one of the very first circuits that IBM researchers published using the first available quantum computers, right, on the cloud. As you can see, it's just 4 qubits, and the depth is very small. The big circuit that you see on the screen that you can barely tell the quantum gates of, that's the circuit or one of the circuits that were run for the utility scale experiment that I showed in the paper before. And this change has happened within less than 10 years, right? So this is where we are, right? And this is kind of where we're gonna go. So we want, as a field, we want to show that these kind of huge circuits can actually lead to results that are valuable, right? Because this is the way to survive and the way to succeed. Since the publication of that paper in the cover of Nature, there has been a number of other papers published also on this scale, right? And this is just a non-comprehensive list, but there are not so many more than what I'm actually showing here. So what is the problem, right? Like what is actually preventing people from running at these scales? And this is what I want to touch base with you in this talk. So just to summarize, what happened is that thanks to the capabilities that were developed in this paper, disruptive change happened, right? We were, as a field, like all of us, not only IBM, universities, research centers, they were just moving along this small line, and then suddenly we jumped all the way here, right? And people started actually running experiments at scales that were inaccessible before, right? Okay, any questions up to this point? All good? Okay, kind of quiet audience today. So with this, we kind of defined what we call the utility scale, right? The utility scale, I think, is very well summarized in this picture that you have here on the left of the screen. Well, your right, my left. So eventually, at the end of the day, we want to reach this frontier, which we call quantum advantage, right? We all know what quantum advantage is. I don't think there's a need to explain that. So the utility scale is kind of like the frontier around quantum advantage, right? One very important thing to notice is that the frontier only extends to lower circuit depths. It doesn't extend to lower number of qubits. And the reason for this is that in principle, with classical computation, if you have enough memory, you can simulate as much depth as you want, right? So depth is not an issue. Like you need to break the barrier of the number of qubits in order to approach this advantage frontier. All right, so this is kind of the context, the lay of the land, you might, of where the field stands right now. And so for context, what my team has been called for within this collaboration with all the Basque ecosystem is to allow people to move from what we call practitioners or to utility, right? So we have identified the same way that we identified these different categories of problems, right? Where we had problems that were solvable, problems that were interesting, and then problems that were timely. This is a very similar breakup, right? We have people who we consider learners. This is the people who are still kind of getting acquainted with the field of quantum computing, understanding what things like channels are, circuits, different algorithms. And once they reach that level, then they are what we call practitioners, right? They're capable of doing their own research, putting out their own experiments, and working in the field. But in order to get to this utility scale, you kind of need specialized knowledge, right? You need to know something a little bit more than what you need to publish other papers, right? There's a gap there that needs to be covered. And my role within this collaboration is to enable you to get all the way to utility and start using the systems and our capabilities to the largest extent possible. No questions? All right. So what do you need in order to reach this utility scale? there are two main things. Okay, this is the second thing that I want you to get out of this talk. The first is the distinction between the types of problems, right? And that some problems might be interesting but not timely, and we need to focus on the ones that are timely today. The second one is what are the ingredients that you need in order to achieve this utility scale, right? First of all, you need to be able to run quantum circuits faster on quantum hardware, right? This is what IBM is specializing on and what we are really, really good at, right? We're improving the hardware, we're improving the software that we have around the capabilities so that you can, in principle, submit things in an easy way, an uncomplicated way, and get results that are meaningful, right? And then there's the second part, which IBM cannot focus on basically because we don't have infinite resources or infinite time, which is once you have like exploring the different problems that you may want to solve, the different applications, right? And mapping them to the quantum formalism in a way that is actually efficient. Because there are many different ways to do this mapping, and if you don't find the right way to do that mapping, then you're kind of doomed from the beginning. So these are the two different aspects that you need to be very, very aware of. And the two of them are equally important. Like if you don't do this part correctly, no matter how much power you throw here, how much you try to do things like error mitigation or things of that sort, you will not be able to get far enough. And the same way is like in the other way around, it's exactly the same, right? If you do the right mapping, but then you don't use the capabilities in the right way, then you also won't be able to get as far as you probably need to get. So again, I already mentioned that the mapping part is kind of the work that we're trying to do with you, because we cannot address that, of course, and because this is a common effort that we all need to do together. So let me give you an example of what it means to do mapping, and this is the third and last thing that I want you to get out of this talk. And then after the next couple of slides, we can move to the demo. The last thing that I want to get you to get out of the presentation is how do I start thinking about this mapping or this problem definition in a way that sets me in the right path towards solving something that is meaningful or beyond classical capabilities, right? Since you're not asking many questions, I'm going to ask that question myself. Who knows what that figure on the right side of the slide represents? Can you? I think you were the only hand. So
Shit. Yeah, sort of. That is like wrongly described graphene because it's a heavy hex.
It's a heavy hex. Yeah.
So the difference between a hex and a heavy hex, I guess, assuming that you can call that a hex, is that you have the corners are coordinated with three paths, while the ones in the center, the dots in the center, are heavily by coordination.
Yeah.
And that is the architecture of the IBM these computers, right?
Exactly. So what this represents here, as Nicolas said very well, is the topology of a quantum device from IBM today. Every single quantum device at IBM has the following topology, and the only thing that changes from device to device is maybe you have more hexagons here, but the whole lattice looks like an hexagon. Every dot that you see would be a qubit, and the edges represent connections between qubits, right? What this means is that if in your problem you define it in a way that you need to make this qubit and this qubit interact, you're kind of in a really bad spot, because you're going to have to start swapping the qubits around, and at the end of the day, for one interaction, you're going to have 1, 2, 3, 4, 5, 6 swaps just to make one interaction, right? And we see this every single day in problems in the archive. If you take a look at it and then you do the transpilation, people end up having circuits with more swaps than actual interactions, physical interactions carrying physical meaning, right? And this is the main reason why when we show that curve, people were not able to get as far as they wanted, right? Because their definition was wrong from the beginning, right? So traditionally, and this is kind of what this slide summarizes, traditionally people have been looking for, they first defined a problem and then they started looking for mappings, right? Like, okay, I now have my problem, this is what I want to solve, how can I map it to the lattice that we have here? And we have a lot of tools for doing what we call transpilation. which is essentially just this mapping between something that can be that is logically correct and something that is also physically correct, right? Can be run given the hardware topology, right? So people did it that way at the very beginning, right? With the paper that I showed before, the main realization that came is that we need to bring knowledge about the hardware from early on, from the problem definition and problem design, in order to get further, right? What this means is that when you're defining the problem, if you're able to actually understand the hardware that your problem is going to be run on afterwards, and bring in the notions of what are the advantages of this hardware and also the limitations, right? And basically work around these advantages and harness the advantages to the full extent, then that's the way that you can use these machines to achieve something that probably no one has done before. Right, I think this is my last slide. Yeah. So within this notion, and just to make this very, very clear, and IBM have been architecting all the problems that we solve and even our software in 4 distinct steps that we call a Kinsky pattern. The first step would be this mapping or definition of your problem, right, that I have already explained. The second part would be to optimize that problem so that it can run more efficiently on the quantum hardware. And what you need to understand, again, coming back to that third point that is very, very important. I'm sorry if I'm repetitive, but this is very, very important. And a lot of people get it wrong. No matter how much optimization you throw at a problem, if your definition is wrong, you're going to be bounded. Like you're not going to be able to do better than a certain amount, right? So it's important to get your definition right first and then optimize, and not the other way around. The third step is to run your executions. And for this, we have been putting a lot of efforts in coming up with this thing that we call the runtime primitives. These are basic computational workflows that you can just send a workload to, and they will give you results right away. So it will take care of everything and will run everything for you in a way that's very efficient. We have 2 of them. One is called sampler and other estimators. Have any one of you heard of this before? One person? Okay, a few more hands. Okay, so about, I would say, 5 or 6 people. All right, so let me just give you an example of what these primitives are capable of. So this estimator primitive here, you can send it a circuit, right? It's preparing a quantum state. You send even a parameterized circuit, right, with a bunch of parameters that you can later bound. You send a bunch of observables that you want to measure, and internally, the estimator will look at which observables commute with each other, what's the minimum number of circuits that you need to execute in order to get an expectation value for every single observable. It will bind all the parameters, also see if there are any efficiency that can be gained from parameter binding. It will take care of all of that, and it will give you a result back. So that you don't know. When I was doing my PhD, this may sound very easy to do, a very easy thing, but when I was doing my PhD, I think the largest amount of time went into actually writing the functions that did just that, which is something that maybe when you're doing things on paper is kind of tricky, right? Mm-hmm. And then the last step in this process would be basically once you get your results from the quantum machines, you just post-process, combine things in the way that you need to combine, and get the readout and the intelligence about the physics that you're trying to achieve. So IBM focuses on these 3 last steps very heavily, and we have a lot of tools to help you in your journey through that. And basically, the question that remains open is, how can we do this? What's the problems that you're interested in solving, right? And for those problems, how can we define them in a way that we can run them on quantum machines efficiently? And of course, part of step 4, which is what kind of physics do you want to get information about? So this is the slides that I had prepared for today. I have a brief demo as well, but I think this is a good moment to make a pause for questions if there are any.
Why the hexagonal layout for the qubits?
That's a fantastic question. So let me repeat that in case the microphone didn't get that. So the question was, why do we have this heavy hex lattice methodology for the hardware? There were many different considerations for this. I can only list a few. One of them is future error correction, right? At the end of the day, we may not be able to do error correction today because the errors in our hardware are, not small enough so that we overcome this error threshold theorem. But at some point, we'll be able to do it, right? And so the expectation is that this kind of lattice will help towards that. Again, I'm happy to share papers with you where this was explored and developed, but that's one consideration. Another consideration was to reduce a certain type of noise called crosstalk. I don't know, have you heard about crosstalk noise? Maybe raise your hands. How many of you know about this? I think 1, 2, 3. All right. So crosstalk is a kind of noise that happens when something is happening in one qubit and another qubit is affected by that thing in very layman terms, right? So this kind of topology reduces the crosstalk error, at least for the superconducting qubits that we have in our hardware, right? I'm going to leave it there. There are a number of other considerations that have to do also with connectivity and stuff like that. Try to have some qubits which have connectivity to 3 other qubits and others that have 2 without, harming too much the number of applications that you can run, right? So it was a very difficult optimization problem to come up with this, and it took a number of years of iteration and looking into different things. And this is kind of what we conversed in collaboration with other researchers. That was a fantastic question, by the way. Right?
But have you tried? I mean, the crosstalk can be eliminated also if there is a lack of symmetry in the pattern. Let's say like Penrose tilings, which are symmetrical, but at the same time are quasi-periodic. So should be something like an implementation to this instead of hexagonal structure is too strange. I mean, I don't know. I don't know a lot of things about this, but just about curiosity.
Yeah, that's a really good point. So the point is that if you have structures which are not so regular, then the crosstalk can be actually minimized or even eliminated, right? That's kind of your point. I'm not a hardware engineer, so I may not get all the details right. But the idea is also like you not only need to optimize for reducing crosstalk, right? You also have a number of applications that you need to run. And for that, having some sort of symmetry is actually beneficial, right? So when you're doing things like this optimization process, for this, you actually need to have a coupling map, and having certain symmetries allow you to be able to do maps and swaps in a more efficient way and find solutions and optimizations that are tractable in a sense. Whereas with something that is completely random, the process of optimization sometimes becomes harder, right? Again, I'm not a hardware engineer, so I don't know all the details, but I know for a fact, because I've worked on some of the optimization tools, that you can use some properties of the symmetry to make it better. So it's a multi-objective optimization, right? You not only need to optimize for one thing, you need to optimize for multiple things, and sometimes those things contradict each other, right? If you optimize too much for one, you make the other one very bad. So this was a very difficult problem to address. Other questions? Yeah.
So from the tensor network's point of view, what are the advantages or disadvantages of using this lattice structure? Like, is it easy to simulate in tensor networks, or it could pose some difficulties?
That's a really good question. So the question again was having this hexagonal topology from the point of view of simulating stuff using tensor network approaches. What does it mean, right? I wasn't part of IBM when this was developed, so I don't know the details. I don't think, or at least I haven't heard of tensor network consideration being brought into the picture. Basically, because what we're focusing on is optimizing the quantum workflows. We're not trying to do something that necessarily has the classical capabilities in mind. We're trying to build new capabilities, right? I believe there are some results of people trying to simulate this kind of topology using tensor networks to, better or worse results. But again, our focus is kind of on trying to optimize things from the quantum side and not so much from the classical capabilities. Does that answer your question? Okay. Yeah.
I can. Can you explain what that utility and advanced 7 mean?
These.
Yeah, the beginning. You were assuming that everyone understood that.
Okay, yeah, maybe you're right. Okay, so I think the question is to try to explain a little bit more of what this utility scale entails, right? Okay, so again, utility, to recap from what I said before, is kind of this frontier that's close enough to quantum advantage, meaning you're close enough to solving problems that are not addressable using classical resources, right? Advantage is when that's defined and it's very clear, like I cannot run this on a classical device, period, right? Like
You know, like well-defined problems that will represent this advanced material.
yeah, it's a very difficult definition to have. Like giving you a very precise definition is actually extremely difficult, and I know this because I've been banging my head against the wall for like 2 months trying to come up with a perfectly scientific definition of what this utility scale is. It's not, the definition is not like that, right? It's more of a frontier definition. It's something that classical computers really struggle in finding solutions for, even though they may actually find it. And the reason why it's very difficult to give a proper definition for it is because the classical capabilities are not static, right? Like as time passes, people come up with new classical techniques that allow you to like push classical capacities a little bit farther, right? And that dynamic definition of what we mean by a classical capability means makes it very difficult to give a very precise definition of utility, right? The way that we define it, just to make it very simple, is basically something that runs around 100 or beyond 100 qubits, right? And with depth, you know, let's say beyond 50 or something along those lines. 2 qubit gate depth.
500 qubits.
Because once
like a breakthrough or like a
Mhm.
here beyond that you can do everything. So why is that my number?
I mean, the 100 qubits is because if you do numerics and try to figure out, if you try to simulate something classically using for 100 qubits, just the amount of memory that you need is so vast that classical computers just cannot compete, right? You would need something like Argon's huge computer that they just built with HPC capabilities, right? Again, this definition is not very precise because you can always use tricks to reduce the amount of memory that you have, and there are breakthroughs in classical simulations that allow to reduce the amount of memory that you need to use for certain problems, right? Like harnessing certain symmetries of a certain problem, things along those lines. That's actually what happened when they published this paper. I think within the follow-up months, people started showing how you could actually solve that using classical resources, right? But at the time of publication, we were collaborating with a team of experts on tensor network simulation, stuff like that at Yale, that just had no idea how to simulate that. And all that they could do was approximations, right? Following up to the work, people started figuring out ways of addressing that. But even the people who figured out how to solve it classically also said, hey, but if you change your problem definition in this small way, then we're doomed. Like this technique no longer works, right? So that's the signature of utility, is that hardness, not impossibility, but that hardness and replication with classical methods. Is that a fair enough answer, you think?
Not really.
Okay, we can talk about it later.
I know that you have like a very well-defined problems that you want to solve, but you know they cannot be done by classical computing. So I guess you define like goals or breakthroughs where to go. And really it's like a more diffuse area from here.
It's a little bit diffused as you mentioned. I'm happy to discuss with you later if you want on more details. But yeah, the definition is a little bit difficult, partly because we also don't know what advantage is exactly, right? Complexity theory is difficult matter. All right. Any other question? How much time do we have left?
We usually schedule seminars for 1 hour approximately.
Okay.
But,
I have a technical question
Yeah,
regarding the sampler and the primitives from Qiskit. For example, you said you can measure the expectation value of observable, but how many times this expectation value is measured? One time, two times, many times? Because as much as I understand, it's a statistical value, not the real observable value.
Yeah, that's a good question. So what you do is you essentially you prepare your state using the quantum circuit that is submitted, and then you make certain measurements in certain bases depending on the observable that you want to compute, and then you repeat that process several times, right? You get a readout. So just imagine that you have the Stirner lag experiment, for instance, right? You prepare your perfect superposition, right? Your spin pointing sideways, right? And then you measure that, and you're gonna repeat that process so many times that you're gonna have a distribution of how many times you actually read a spin up and how many times you read a spin down. And then from all those measurements that we call shots, you get a statistics out of that, and that's how you compute your expectation value. Right? That was a really good question. And so that process that seems simple enough, once you have like a plethora of different observables that you need, and some of them commute and some of them don't, and you need to have different circuits depending on whether they commute or not, that becomes very cumbersome. And again, my thesis that took me a lot of time just to be able to figure that out in code and get the right results. And now it's with the estimator, it's just a matter of saying this is the observable or the observables, and this is the state, right? State you're gonna get with this quantum circuit, and off you go. Everything's taken care for you.
For example, you mentioned you can put your observable and also some parameters. How many parameters can?
As many as you want.
As many as you want.
As many as you want. Yeah. I mean, there are probably limitations, but these are classical limitations. Like if you want to have, I don't know, billions of parameters, right? And every parameter is a floating point. How many gigabytes of data do you have to transmit to bind the circuit, right? Probably a lot, right? So there might be some network limitations to that, but
well,
in principle, as long as you can submit through the network, it should be good to go.
Yeah, because this question is related to some models in which we want to use not just one, but a couple of parameters, a family of parameters, etc. So just
No, you can have like. Let me go back to this thing. So in here, like this was a parameter that now is binded to minus pi halves. And this was also a parameter, and this was also a parameter. Now see how many gates you have in the circuit. Every purple gate that you see in the circuit is one parameter. So yeah, a lot of parameters.
Okay. Thank you.
All right. Anything else? All right, so I have a small demo. Well, no, actually not small at all. It's quite a large demo that I don't plan to go through entirely, but just to show you some of the things that you can do with the primitives in these last 3 steps, right? That and how we provide from IBM, how we provide support for you to do those things easily. All right. So we begin by defining a bunch of circuits, right? So we have run this demo on a number of different circuits. The reason being, we wanted to show that these capabilities actually work not only for one circuit, right? This is something that happens a lot of the times. Like you find out something, and that's something that you find is fantastic and it's brilliant, but it only works for your circuit, right? We want to show that these capabilities were actually able to perform well in different scenarios, right? So for this study, we actually used a quantum approximate optimization algorithm circuit. How many of you have heard of this? This one's kind of famous. Raise your hands. QAOA. All right. Well, it's a type of circuit. It's very, very well known. It's used for hybrid workflows where you're doing classical optimization, but evaluating your function on a quantum computer. So you evaluate an expectation value using a quantum processor, and then on top of that, you do classical optimization over a number of parameters. Then the other one is the circuit that was used that I was showing the slide before for that utility paper. which is just some transfer field Ising model dynamics, where they were just doing some Hamiltonian evolution and reading out relevant physics from it. And the last one is a many body localization circuit, where we're trying to compute local integrals of motion in certain system. So these were the problems that the types of circuits that we tried to address. And again, I'm not going to go through all the definitions. I can send you a link to this notebook if you want. The first one was defined in this paper in 2014. And here's how you define the circuit. It looks something like this for 4 qubits, of course. We did it for a larger number of qubits. Then this other paper was the UDIT paper that I already talked about. And then the many-body localization paper was this one from July of 2023. And the circuit looks something like this. So again, they're all relatively similar to each other. Another reason why we like this kind of circuit is because they're very dense. If you're thinking about how they look like, the particular circuits that we run in these experiments were one-dimensional. We didn't go for a two-dimensional structure because what that gives us is very, very dense circuits where you don't have qubits which are idling for a long time. And you'll see why that's relevant in a moment. All right, so what did we do in this particular experiment? We ran all of these circuits, but we made a small modification to the circuits, which is because we didn't know exactly what results we were going to get out of that particular simulation, especially once we went into like 64 or 80 or 100 qubits, like doing classical computation to know exactly what expectation value to get out of it was just not possible. What we did in order to just showcase the capabilities is we declared the circuits as mirror circuits, where we have here the unitary that we want to compute, and then here is the inverse unitary, right? So by the end of this execution, we are supposed to go back to a readout, which is entirely deterministic, and it's just what we had at the beginning here, which says all qubits in the 0 state. So if the circuit performs correctly, once you get to the end and do your readout, you're supposed to just read 0, 0, 0, 0, 0, 0, 0. Otherwise, you've had some kind of error or noise along the way, right? Okay, so this is basically the experiment that we carried out. Any questions about the experiment so far? Okay, so there was a question in the back. So we use some random parameters to your question of the parameters before. You can see here we just did a random uniform from -pi to pi, and we bounded, in this case, I think was 49 parameters, because this one is independent. And we just bounded all of that completely randomly to get some kind of result. Okay, so that was step one. In this case, very easy. We don't want to go into like exploring physics. We just wanted to have a problem well defined so that we can show you some metrics of what you can achieve with this. Step two is to optimize your problem. Now, to optimize your problem, there's several things that come into play. I've listed here some of them, but basically, first you need to transpile your circuit. This is the very, very first step. It's very important. What this allows you to do is to move from a circuit which is purely logical, right? I was showing before, let me go back. I was showing before this heavy hex lattice, right? So in principle, your logical circuit could have gates between here and here, and here and here. In our case, it was just a 1D chain, so there were no all interactions would be aligned. And so transpilation means find a line within your topology that is optimal for running the thing that you want, right? So you could look at things like, what's the error rate in this qubit? What's the error rate in this edge? And then you find the best possible line across your topology so that your results are better. That's part of the transpilation. The part of transpilation is to translate the gates into gates that the hardware understands, right? If you want to run a C0 gate, for instance, that gate may not be supported by the hardware, and the hardware may do those kinds of gates in a different way. So you need to write the C0 in an equivalent way based on the hardware native gates that are supported. So that's transpilation. This is the first part and very, very important. Like doing good transpilation gets you a long way as well. And then the second part and third part, if you might, is you can perform certain error mitigation and error suppression techniques on top of your circuit, right? I should have brought a kind of a schematic to show this, but basically we divide these error addressing techniques in 3 categories or three different types. One of them is error correction. You have heard of that already, and it's not available today, so get that out of the way. The other 2 categories are error suppression and error mitigation. The main distinction between the 2 of them is, well, the distinction between those 2 and error correction is that these techniques don't remove the error. They either make the error smaller or let the error happen, but then somehow correct or reduce it afterwards in a way, right? So error suppression usually does the former, which is that you just try to make the error less prominent in your circuit as it runs without completely making it vanish. The error mitigation one, you just let the error happen, but then in smart ways, you remove it from your results afterwards. That's error mitigation. And so here you have several different techniques that you really don't need to know much about in order to use, because you can just ask the estimator to do them for you. Of course, the more you know, the better, because that means that you can define your circuit with this knowledge in mind, and then your error mitigation or suppression would work better. Techniques for this are, in the case of error suppression, we have things like polytwirling and dynamical decoupling that I have some explanation of what they are afterwards. And then for error mitigation, we have things like zero noise extrapolation and real error mitigation in this particular form, which is called T-Rex. Let me just move forward and I will show you what they're about. Okay, so just for reference, this is the circuit, the virtual circuit that we wanted to run. So when we do transpilation, that virtual circuit becomes something like this. So you see that before we had those control set gates, and now everything's expressed in terms of this weird gate called an ECR gate. No need to understand exactly what the ECR gate is. It's just another 2-qubit gate, and it's equivalent to a C0 and equivalent to a control set up to single qubit rotations. And the qubits, the virtual qubits, have already been mapped to particular places in the heavy hexagonal lattice that we had in our hardware. Okay, polytwirling. This is the first technique to reduce the noise. This is an error suppression technique. So what polytwirling actually does is it makes your noise smaller as it runs in the, well, not as it runs in the circuit, but it makes the effects of your noise smaller during execution. How many of you have heard of this before? Like, show of hands, polytwirling? One person. Okay, cool. Polytwirling is actually, it's conceptually easy to understand what is happening. It's a little bit harder to derive theoretically why this is the case. Okay, so just bear with me. I'm going to explain you the former, and I will send you some references if you actually want to go through the math. So twirling is also known as randomized compiling. It's a very well-known technique that is used for converting an arbitrary channel, whatever channel you want, into another type of channel, right? Polytwirling is a special kind of twirling that is based around the Pauli set. So what that means is that when you do polytwirling in particular, you're going to convert any channel that you have into a Pauli channel. It's a special kind of channeling in quantum. How many of you know about Pauli channels? Let me maybe ask that question first. Raise of hands. No one? Okay, one. Okay, the same one that they already knew about polytwirling. So how many of you know what a channel is in a circuit? One. Okay, how many of you know what a gate is in a quantum circuit? Okay, cool. All right, a few more. A channel is some sort of generalized gate, right? You know that gates need to be unitary, right? Channels don't necessarily need to be unitary. Gates are always information preserving. So a gate represents a transformation that preserves entropy. a channel doesn't need to preserve the entropy, right? It can represent information loss, right? That's the main difference between a channel and a gate. Otherwise, you can think of a channel just as a fancy gate, okay? And a Pauli channel is a channel that can be represented as Pauli gates, as some kind of like random distribution of Pauli gates, right? So for instance, imagine this thing as this is a channel, okay? This is what it's represented is a noise channel. If this was a Pauli channel, this would be equivalent to when I'm running my circuit and I get to this gate, I apply a Pauli randomly. Okay, that's, as you see, that's not unitary, right? Because you're doing something randomly right there, so you're losing information. But that's in of itself a Pauli channel. That's it, nothing more. So what Pauli twirling does is it converts channels into, it projects them into the Pauli channel space, basically. So to understand how it works and how it's implemented, you just need to know two things. The first one is that when I do this Pauli twirling, so this is a noise channel, then I apply Pauli's, the same Pauli before and after, and I do a sandwich. And I apply them randomly. Like this is a random Pauli, and this is the same random Pauli that I applied before, and I repeat this process multiple times. Then what this thing is gonna have is the effect of converting this channel into its Pauli form. So it's gonna project this channel to a Pauli-like channel. Yeah.
By applying a Pauli, you mean a Pauli string?
Yeah, this could be as many qubits as you want. So this could be, if you just think of this as one qubit, then this could be either the identity, an X gate, a Y gate, or a Z gate. If you have multiple qubits, then that repeats over the different qubits that you have. So yeah, in multiple qubits, it would be a Pauli string, basically. Yeah. Okay, so this, just take it for granted. I can send you the derivations for this. It takes a couple of pages of math, and you can show that. The second thing that you need to know is, okay, this is the unitary that I want to apply, right? So I need to find some kind of sandwich in this form such that my unitary is preserved, right? So let me actually scroll up a bit. So in the case, for instance, of a CNOT, right? This is the unitary that I want to apply, but you can do the algebra yourself. This thing is exactly the same as this thing here. Like the unitary that it represents is exactly the same unitary, right? So the second thing that you need to know is, okay, given the unitary that I want to apply, what sandwiches of this form preserve the unitary? And these two Paulis don't need to be the same here. That's why one is P and the other one is P prime. If you rearrange the gates, basically what you mean is that having a Pauli here followed by your unitary is the same as having first the unitary and then the other Pauli. So you can commute these two by virtue of like changing the Pauli or permuting the Pauli string that you have. So these are the two things that you need to know. Then the way that you actually apply Pauli twirling is very simple. You have a noisy U, right? So this is the perfect U that you want to implement. This is some noisy version of that gate that I'm representing as a noise channel and the ideal U, right? So using these actions here, it's very easy to show that if I just apply P and P prime here randomly from the set of all P and P primes that preserve the gate in this way, then that has the effect of getting the noise channel into a Pauli noise channel. The reason why this is very effective for reducing the noise is because, for instance, if this noise is coherent noise, the amount of errors that this is going to induce grows quadratically, whereas Pauli noise only grows linearly. So you're not destroying the noise, you still have noise, but now it's decreased. It has other second-hand effects that are very useful for a number of things. But anyway, this is basically Pauli twirling. And again, you can figure this out for like, this is a very, very easy matrix algebra problem of, I have the matrix for the CNOT and I know what Paulis are. You can write a very simple Python script and it will spit you out all of the Paulis that follow that. How many of you know what a Clifford gate is? Show of hands. a couple of people. 3. Clifford gates are special kinds of gates that have a property that any Pauli can be permuted to the other side. So when your unitary is Clifford, then this is particularly useful because you are not limited. See, this is basically if for every single Pauli you can do this, then this gate here is said to be Clifford. If the gate is not Clifford, then there are some Paulis that are just not going to be able to permute through. So when your unitary is Clifford, then this technique works particularly well. This is the case for every single 2-qubit gate that we have in the hardware. And this is code to do Pauli twirling. Readout errors can also be mitigated in a very similar way. This T-Rex technique is very, very similar to the twirling technique that I explained before. But you're applying that twirling on measurements instead of applying it on unitaries. You're basically randomly substituting just a measurement gate with a NOT gate, the measurement, and then a classical NOT. So these two things are the same. I hope you can see that. By choosing between which one you apply randomly, you also what you basically do is you diagonalize the noise channel, and then because it's diagonal, you can invert it later, and that way is how you mitigate the noise. Again, kind of lengthy derivation, but then zero noise extrapolation, again, a very, very cool technique. The way this one works is by running your circuit in different levels of noise, increasing your noise. So you make things worse and worse and worse and worse. And then you get data points for different levels of noise and you extrapolate back to 0. So you say, okay, if my noise level was 1 and I was getting this result, and my noise level was 2 and I was getting this result, then what should I expect from the noise level 0? Again, very simple qualitative thing, but becomes a bit more difficult in practice. And then the last technique that I want to show you is dynamical decoupling. This one addresses crosstalk, actually, effectively. So what this does is crosstalk usually happens when you have idle qubits. So you see here that for a little bit of time, this qubit is not doing anything, it's idling, while these other qubits have gates happening in them, right? So what this induces is that the operations happening in these qubits, again, layman's terms, they leak into these other qubits and they produce rotations and errors. So the way to address that, or to mitigate that in a sense, is to insert some sequence of operations here that amount to the identity. So they are globally they don't do anything. For instance, you negate twice, right? You do not and then not again, but that makes those qubits stop idling, and that kills the noise. So with all of those techniques in place, you can actually configure them through the estimator. This is a very lengthy and comprehensive table of things that you can turn on and off regarding those 4 mitigation techniques. And it allows you to get results for the problem that I showed before, as follows. And this is basically the end of the presentation. Let me see, can I? Yes. Okay. So these are the results that you get when there's no mitigation, right? So this is the ideal result that you should get, expectation value of 1. And you see that with no mitigation, your results are roughly 0.6. And then as you keep adding mitigation techniques, your results start getting better and better and better. And then by the end of the day, when you apply all of the mitigation techniques, you are actually very close with more than 90% fidelity of the result that you actually wanted to get. And this you can do effectively just by applying some configurations in the estimator primitive. So this is what I had in terms of the demo. There are more details here as to things that you can do and whatnot, but I think that that's a good summary for now.
Thank you very much, Pedro. So we already had several questions in the meantime, but if you have some additional questions for the second part of the talk, please go ahead.
No, I'm just curious. I mean, you said that I don't see much improvement there. Basically, it's only the extrapolation that works in the end.
That's a really good question. I have to say that I did it on purpose because I wanted to get this question. Remember when I said at the beginning that the circuits that we chose were very dense, and that the fact that they were very dense made the qubits idle very little, and that was intentional? What that the effect that has is that dynamical decoupling is almost worthless, right? Because your qubits are already not idling. So there's nothing really to mitigate on that front, right? That explains why this and this are very similar. Now you have to agree with me that other than these two, this is larger.
Yeah.
This is again a little bit higher, right?
Sure, it is.
So yeah, this one here is explained by that. T-Rex, there are nuances, okay? This is the readout, so the readouts are pretty good, and that's why there's not much correction here because the readouts are already fairly good. This is twirling. Twirling doesn't do much because again, what twirling does, it just makes the noise have a different form, right? So the difference that you're seeing here with twirling is just going from quadratically accumulating the noise to linearly accumulating the noise, right? And because the noise is small already, the correction that you get just by twirling alone is very small, right? And then CNE corrects a lot. Let me get to that in 1 sec. I also mentioned that twirling was beneficial and had second-hand benefits other than this notion of making the noise accumulate linearly instead of quadratically, right? One of the benefits that it has is that Pauli channels are what we call unital channels. Now, you probably haven't heard of this, but what a unital channel means is that as you apply more and more, your state goes to the maximally mixed state and not to something else. Like there's certain noise, right, that may, for instance, make your one state decohere all the way to one, right? That's not unital because the more noise you have, the closer you are to the zero state, right? Unital noise takes you to the maximally mixed state. This is very good for CNE, right? Because if you're always tending to the maximally mixed state, then the noise curve that you get is monotonical. You don't get weird fluctuations in that curve, and that allows you to do the extrapolation very well. Right? Like if you're trying to extrapolate on something that just like wiggles very much, your extrapolation is going to be very poor, right? So the main reason for applying twirling is to make CNE behave better. And then yeah, of course, CNE does a lot. CNE has a lot of power to make things better, but it's also relatively unstable, so you have to be careful when you use it. Because again, you have so much power to correct that if you overshoot or undershoot, you're gonna go very far away, right? I'll leave it there for now. Did it answer your question?
Yeah. Thank you.
There was another question here.
So these techniques are meant to run on many shots, as I understand.
Yeah.
So does it improve if you increase the number of shots?
That's a fantastic question. The answer is yes. There's a trade-off when you apply error mitigation. There's a very well-known trade-off, which is that you reduce your bias. This is what I'm showing here. But to all of you who are maybe like me with a little bit of an OCD, notice that there are no error bars here. And that kind of makes my scientific heart hurt. When you apply mitigation techniques, the error bars grow. You reduce the bias, but you increase the spread. So if you want to account for that, you need to increment the number of shots to make the spread smaller again. So it does have a little bit of a trade-off in that sense. Yeah. Did that answer your question?
I was asking more about if you are getting closer to one.
If you're getting closer to one, when you increase the number of...
I mean, you reduce the variance of the results, but are you moving really the median or the mean up to one, or
By increasing the number of shots, that what you usually do is you you reduce the spread more than reduce the bias. Of course, if your noisy results have a spread which is like this, then this extrapolation may not be very good, right? So by increasing the number of shots and then making them this smaller, then you make it get better results there as well in terms of the bias. But you're gonna hit a limit at some point. Some techniques are unbiased. There's one very famous error mitigation technique called probabilistic error cancellation that I haven't touched base on here. That is supposed to give you estimates that are completely unbiased. But that one is a little bit more advanced. Yeah, that was a good question.
Any other question? So, okay, if not, let me also thank you again, not only for the help, but also for the help that you are providing during these days for all the collaboration projects that are going on. So thank you very much. And so we hope to see you quite often.
My pleasure. If you have questions, I'll be happy to chat.
Yeah, I have no idea why not.